Today we will learn about magnetic materials. Materials are made up of a number of atoms which are arranged in regular periodic fashion. If you take an atom, it consists of a nucleus and the electrons are revolving around the nucleus in various orbits. Here, this is the atomic structure shown here. Here red one is nucleus and the blue one is electron. Look at the arrangement of electron orbits within this atomic structure. The electron orbits are oriented in different directions. The orientation of the electron and the number of electrons present within the atom gives rise to magnetism or non-magnetism in a material. So what is the origin of magnetism? Origin of magnetism is due to two types of motion of electron. One is the orbital motion of the electron, the other one is the spin motion of the electron. This is the orbital motion of the electron. In addition to this, electrons spin about its own axis while it revolves around the nucleus in an orbit. So due to these two types of motions, we get magnetism in a material. Now here this indicates a particular electron orbit. So the minus indicates that the electron. When the electron moves in a circular orbit, it establishes a current. Now I is the current established. Due to this current, there is a magnetic field established. Corresponding to this magnetic field, we get a magnetic moment. The direction of the magnetic moment is perpendicular to this plane of the orbit. Due to orbital motion of the electron, we get orbital magnetic moment, and due to spin motion, we get spin magnetic moment. Now we'll go to the next slide where I'll explain about orbital magnetic moment. As I said earlier, the revolving electron in a circular orbit establishes a current given by I equals to charge divided by time period. Now we get this equation. Here E is the charge of the electron. The negative sign indicates that electron has a negative charge. The current establishes a magnetic field around the circular orbit so that upper surface acts as south pole and lower surface acts as north pole. The orbital magnetic moment is now given as mu equals to I into A, where I is the current flowing in the orbit. Here is the current due to the motion of the electron in an orbit. A is the surface area of this orbit. This is equal to minus E omega 2 pi, in where this is the current part, which I told you already, current part. This is the current. Pi r square is the surface area. So finally we get this equation. Then what is the angular moment of the electron in this orbit? That is given by m omega r square. Here v is linear velocity equals to radius of the orbit r is the radius of the orbit multiplied by the angular velocity of the electron in the orbit. So now what is the unit for magnetic moment? The fundamental unit of magnetic moment is known as Bohr magneton, and its value is 9.27 into 10 to the power minus 24 ampere per meter square. This is the unit used for magnetic moment universally. So in this slide we just continue with the second slide, where orbital magnetic moment is given by minus e omega r square by 2. Here multiplying and dividing by m, and we get e by 2m here, and here this part is just the orbital angular momentum. And the angular momentum associated with the orbital quantum number is given by this. Now we get finally an equation like this. If you substitute here, we get this equation. Finally we get like this. Here mu b is the Bohr magneton, which is given by this value. Now we'll go to the next slide about spin magnetic moment. Spin magnetic moment, similarly we get a spin magnetic moment. So based upon this magnetic moment, we get different types of magnetic materials. About this we'll see next. Before that, I want to explain about magnetic dipole. A magnetic dipole consists of two poles. One is north pole, the other one is the south pole. And these are the magnetic lines of forces. So magnetic lines of force, we can see magnetic lines of force. So depending upon the density of the magnetic lines of force, the magnetic field intensity surrounding this magnet is decided. Any two opposite poles separated by a finite distance constitute a magnetic dipole. Having said about magnetic dipole, what is magnetic dipole moment or just magnetic moment? Magnetic moment is given by this formula mu equals to m into 2L, where m is the pole strength, 2L is the perpendicular distance between the two poles. Also magnetic moment can be written in terms of the current and the surface area of this orbit, as I told you earlier. So unit of magnetic moment is ampere meter square. Following this, we will see some definitions which are related to the study of magnetic materials. So what is magnetic field? Magnetic field, it is the space surrounding the magnet up to which its influence is felt. Its unit is Tesla. That is also known as magnetic field intensity, which we will see later. The next parameter which we should know related to the magnetic properties of the material is magnetic induction or magnetic flux density. It is defined as the number of lines of force passing through unit area perpendicularly. So magnetic lines of force are nothing but magnetic flux. Magnetic lines of force constitute the magnetic flux, which is given by the symbol phi. So unit for magnetic flux or unit for magnetic flux is Weber. Unit for magnetic flux density is Weber per meter square or Tesla. Now what is the formula for magnetic induction? Formula for magnetic induction B is flux per unit area, therefore phi by A. Thereby we get the unit as Weber per meter square. This diagram illustrates how the magnetic lines of force just penetrate or permeate through the material. Now we'll go to the next slide for the next definition, magnetic flux. Already I told you about magnetic flux. So from the equation which I showed you in the previous slide, magnetic flux is given by this equation. Magnetic flux is B into A, that is flux density, that is magnetic induction into area through which the magnetic flux lines enter in the perpendicular direction. These are all very simple fundamental definitions. So what is magnetic flux? It is a product of average magnetic field times the perpendicular area that it penetrates. We'll go to the next definition, magnetization. Whenever you take a magnetic material and if you apply the magnetic field, the material is magnetized. To what extent it is magnetized? That is defined by the magnetization, which is denoted by the symbol capital M. Sometimes in some way it is also denoted by the letter capital I. It is also known as intensity of magnetization. Magnetization or just intensity of magnetization. Anything we can follow. So here it is denoted magnetization in M or intensity of magnetization. So what is magnetization? When you apply the magnetic field to the material, it gets magnetized. The process of converting non-magnetic material into a magnetic material is known as the magnetization. When a material is magnetized, it develops a net magnetic moment. The measure of the magnetic moment only tells about the magnetization acquired by the material. That is how many magnetic moments per unit volume are created when the magnetic field is applied to the material. So the magnetic moment per unit volume is called intensity of magnetization. The unit for magnetization is ampere per meter. So next we'll go to the next definition, magnetic permeability. Magnetic permeability. Permeate. Look at the word permeate. Have you heard of the word permeate? Yeah, from that word the permeability is understood. So the magnetic lines, how much they permeate into the material. The more they permeate into the material, the more is the magnetization that they can acquire. So this is the simple way of understanding the meaning for magnetic permeability, which is also denoted by the symbol mu. Magnetic permeability is the characteristic property of a medium. It indicates the ease with which the material allows magnetic lines of force to pass through it. How much the magnetic lines of forces can penetrate into the material, permeate into the material. So it is also a measure of the ability of the material to accept the magnetic lines of force or to accept the magnetic field within itself. Or in other words, we can say it is the degree of magnetization that a material obtains in response to an applied magnetic field. So this magnetic permeability mu is given by mu r into mu naught. Mu r is the relative permeability of the medium. Mu naught is the permeability of free space, which is 4 pi into 10 to the power minus 7 Henry per meter. Now we'll go to the next definition, magnetic field intensity H. The unit for magnetic field intensity is also ampere per meter. What is magnetic field intensity? Magnetic field intensity at any point in the magnetic field is the force experienced by an unit north pole placed at that point. Always we say magnetic field intensity at a point, because if you take a magnet, surrounding this magnet there is an area. Within that area a force is always felt. That force is known as the magnetic field. the force surrounding this magnet is different at different point. That's why we have to calculate the magnetic field intensity at a particular point. Magnetic field intensity closer to the magnet is very high. When you move away from the magnet, the magnetic field intensity decreases. So the magnetic field intensity at any point is the force experienced by an unit north pole placed at that point. Unit is ampere per meter. Then comes the next definition, magnetic susceptibility. From the word susceptible, you can understand how much the material is susceptible to the magnetic field to which it is subjected to. The symbol is chi, which is equal to intensity of magnetization by applied magnetic field. So, chi is defined as the ratio of M and H. It is the ratio of M and H. That is M by H. M has the unit ampere per meter, H also has the unit ampere per meter, so chi does not have any unit, it has no unit. Then, how will you define magnetic susceptibility? It is the degree of magnetization of a material in response to an applied magnetic field. For a given H, how much M is produced? That is chi. So, M is directly proportional to H, M is equal to chi into H. From that, you get the relation like this. Then M is magnetization here, H is applied magnetic field. Its value is, the magnetic susceptibility value is maybe 0, it may be positive or negative. Next we go to the types of magnetic materials. Magnetic materials are classified into 5 groups depending on their response to the magnetic field. They are all diamagnetic materials, paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. So before that, let us recall what are the definitions we have seen. The definitions are magnetic flux density, magnetic field intensity, magnetization, magnetic susceptibility, magnetic permeability. These 6 parameters are very essential to understand the properties of magnetic materials. Depending upon the magnetic permeability, magnetic susceptibility, we have 5 types of magnetic materials, which is shown in this slide. Diamagnetic materials, paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. Each material has its own distinct feature. Now we will see about the property of each material and some examples in the coming slides. First, let us start with diamagnetism. Diamagnetism. It characterizes the substances that have only non-magnetic atoms. In diamagnetism, there are no permanent dipoles. So there are no permanent dipole moments. Why there are no permanent dipole moment? The reason is given here. An electron moving around the nucleus results in magnetic moment that we know. These electrons are moving in different orbits. The orbits are oriented in a different way. So due to different orientation of various orbits of an atom, Due to different orientation of various electron orbits within an atom, the net magnetic moment is zero in diamagnetic material. We know due to each electron orbit there is a magnetic moment. The orientation of the electron orbit within an atom in a diamagnetic material is in such a way that the resultant magnetic moment due to all these electron orbits becomes zero. So there is no net magnetic moment in a diamagnetic atom. So all these we say when there is no external magnetic field applied. If you apply the external magnetic field, that is if you apply the magnetic field to the diamagnetic atom, what is going to happen? So when it is applied, the orientation of the orbit changes. So when the orientation of the orbit changes, the direction of the magnetic moment also changes. So the net magnetic moment now is not equal to zero. It has some value, but that value is very low. Net magnetic moment is very low, but there is a magnetic moment. This is known as induced magnetic moment. Why it is known as induced magnetic moment? Because previously there is no magnetic moment. Now if you apply the magnetic field, a magnetic moment is induced due to the rearrangement of electron orbits within an atom. And what is the direction of the induced magnetic moment? It is in a direction opposite to the direction of the applied field. That is, the induced magnetic moment opposes the magnetic field which produced this magnetic moment, which you can understand from this diagram. Now you see the magnetic lines of force are repelled outside. In this diagram, the arrow mark indicates the magnetic field which you apply. So when the magnetic field is applied, a magnetic moment is induced, but this induced magnetic moment repels the applied magnetic field. So all the magnetic lines of force are sent outside the diamagnetic material. So this is the special property of diamagnetism. Next, we will see few more points about diamagnetic material. The magnetization induced by the applied magnetic field is very weak and the magnetic lines of force are repelled. That is what I explained in the previous slide. This magnetism also exists in substances with magnetic atoms but very weak and completely masked by the contribution of magnetic atoms. Relative permeability is slightly less than unity. The magnetic susceptibility is independent of applied magnetic field strength. If you take all the materials in the universe, all the materials they show diamagnetism, but diamagnetism very less, it is not that much noticeable. Magnetic susceptibility of the diamagnetic material is small and negative. It is small and negative and it is independent of temperature. There are some examples given here. Next we will go to next type of magnetic material, paramagnetic material. Paramagnetic material has permanent dipole moment. That is, paramagnetic atom, if we take paramagnetic atom, there is a resultant magnetic moment. In a diamagnetic atom, there is no resultant magnetic moment. In paramagnetic atom, there is a resultant magnetic moment. Now, if you take a paramagnetic material which consists of a number of atoms, these permanent dipole moment, they are arranged in random fashion, which is shown here. They are arranged in random fashion like this. The paramagnetic substances consist of magnetic atom that possess permanent dipole moment. Each electron in an orbit has orbital magnetic moment and a spin magnetic moment. When the shells are unfilled, there is net magnetic moment. In the absence of external field, the net moments of the atoms are arranged in random directions because of thermal fluctuations. Hence, there is no net magnetization in the absence of applied magnetic field. When an external magnetic field is applied, there is tendency for dipoles to align with the field, giving rise to an induced positive dipole moment that we will see in the next slide. The induced magnetism is the source of paramagnetic behavior. Paramagnetic susceptibility is small and positive and is independent of applied field strength. Spin alignment, as I told you, random. Magnitude of susceptibility is small and positive. So in diamagnetism it is small and negative. For paramagnetism, susceptibility is small and positive. Temperature dependence, independent of temperature. These are the examples. And these paramagnetic materials they satisfy a law known as Curie law. Here, chi susceptibility, chi equals to C by T, where Q is the C is the Curie constant, T is the absolute temperature. This law is known as Curie law. This law is obeyed by the paramagnetic materials. Next, we will see to the paramagnetic material. If you apply the magnetic field, what happens? Here, 3 diagrams are shown. The first one indicating the random spin alignment in the absence of the magnetic field. So if you apply the magnetic field, then these randomly arranged spins, they tend to align themselves along the direction of the magnetic field. Here the arrow mark indicates the magnetic field H. In this case, H is 0. Here you are applying magnetic field. So if you apply the magnetic field, spins are aligned in the direction of H. Now in this condition, if you increase the temperature of the material, what happens? Due to the temperature, the spin alignment is disturbed. So this is the effect of magnetic temperature. Next, we'll see ferromagnetism. Among the magnetic materials, ferromagnetism is one of the important magnetic materials because it has a special feature known as spontaneous magnetization. Even in the absence of the external magnetic field, some substances exhibit strong magnetization. Such materials are known as ferromagnetic materials. This is due to the special form of interaction called exchange coupling between adjacent atoms, which results in spontaneous magnetization of the substance. So if you take a ferromagnetic material which consists of a number of atoms, there is exchange coupling between the adjacent atoms, due to which the resultant spin due to each atom align themselves in the same direction. So resulting in spontaneous magnetization, because magnetization means spin getting aligned in the direction of the applied magnetic field. So this happens, all the spins they align themselves in the same direction, means magnetization is very high. So when placed inside a magnetic field, it attracts magnetic lines of force very strongly. Even if you apply a very low magnetic field, magnetization is very high in the case of ferromagnetic materials. Each ferromagnetic material has a characteristic temperature called ferromagnetic Curie temperature. Below this temperature, the spontaneous magnetization exists. That is, below this temperature, the material shows ferromagnetic behavior. Ferromagnetic behavior means spontaneous magnetization. Above this, the spontaneous magnetization disappears, means ferromagnetism disappears. So if it disappears means what happens? It becomes paramagnetic material. Now I'll erase this. Unwanted. Another speciality about the ferromagnetic material is magnetic domains. Ferromagnetic materials consist of a small regions, a number of small regions, which are called domains. Now look at this picture. Within this picture, you can see very small domains. This image is taken from a microscope. You can see small regions. All these small regions are known as domains. Here a particular region is indicated. Within this domain, the spins alignment, all the spins, atomic spins, they will be aligned in the same direction. What is the need of the domain? The reason a piece of magnetic material such as iron spontaneously divides into separate domains is to minimize the internal energy of the system. Any system should be in its lowest energy, then only it will be stable. So if in the case of ferromagnetic materials, when it is divided into several domains, the net internal energy of the system is minimized. Then only it will be stable. So the formation of domains is merely to minimize the internal energy of the system. Now this slide explains the domains. If you do not apply the magnetic field, what happens to the domains? When you apply the magnetic field, what happens to the domains? How the domains are disturbed? So in this diagram, you can see 4 domains. Within each domain, you can see the arrow marks are in the same direction. Each arrow mark indicates a spin, that is spin due to the atom. So all the spins are aligned in the same direction in this domain. But if you look at this domain, the spins are aligned in the different direction. Now this domain, spins are in this direction. So like this, spins in different domains are aligned in different directions. So if you do not apply the external magnetic field, the total effect of all the domains will result in M equals to 0. That is, magnetization is equal to 0. Now if you take this domain, if you consider this domain or any domain, you can see this, all the spins are aligned in the same direction. This is due to exchange coupling between the atoms within this domain. And this exchange coupling, to align this atomic spins in the same direction, that requires energy. That energy is known as the exchange energy, which we will see later. Now if you apply the magnetic field to this domains, what happens? So here magnetic field is applied externally. H is a magnetic field. If you apply, what happens? When H is applied, spins are aligned in the direction of H. Now look at this, all the spins are in the same direction. This happens for a very high magnetic field. When the magnetic field is low, slight disturbance in the direction of the spin occurs. If you keep on increasing the magnetic field, external magnetic field, the rotation of the spin changes, and finally all the spins may align themselves in the direction of H. So when this process is going on, the area of each domain may change, volume of each domain may change. So volume of one domain may increase, the volume of the other domain may decrease. That depends upon how the spins are arranged in different domains. So and this process of turning of spins in the direction of H is known as magnetization. And I told you about spontaneous magnetization. In the absence of the magnetic field, this is the meaning of spontaneous magnetization. That is, all the spins are aligned in the same direction. Because of exchange coupling, the spins are aligned in the same direction. Next, we will see about the spin alignment in the case of ferromagnetic material. Now look at the spin alignment in the ferromagnetic material. All are aligned in the same direction. This is what we see in one domain. Spin alignment is parallel. In paramagnetism, it is random. In ferromagnetism, all the spins are aligned in the same direction, which we call it as spontaneous magnetization. Such alignment occurs in one domain. So in each domain, this is the case. Alignment is parallel, and all the spins are of same magnitude. In the case of ferromagnetic material, there is a very important temperature known as Curie temperature, theta, denoted by theta, which we will see below. Ferromagnetic materials exhibit hysteresis. About hysteresis, we will see in the subsequent slides. Now, magnetic susceptibility of ferromagnetic material, it is very large and positive. Susceptibility is very large. It means that even for a very low magnetic field, the magnetization is very high. That is, easily it accepts the magnetic field and it gets magnetized. So magnetic susceptibility is very large, means even for a very low magnetic field, the magnetization is high. That is the special feature of ferromagnetic material. These materials obey one law known as Curie-Weiss law, which is the equation for susceptibility. Susceptibility of ferromagnetic material is equal to C Curie constant divided by T minus theta, where theta is the Curie temperature. There is one special significance about Curie-Weiss law. When the temperature is greater than theta, the ferromagnetic material becomes a paramagnetic materials. The behavior is paramagnetism. That is, paramagnetic material means spins are aligned randomly. When the temperature is less than theta, it shows ferromagnetic behavior. That is, spins are parallel to each other. These are the examples for ferromagnetic material. Now we will see a comparison between these three materials: dia, para, ferro, and a normal material. So in a normal material, the magnetic lines, they just enter. In a diamagnetic material, magnetic lines of force are repelled outside. In paramagnetic materials, magnetic lines of force, they are included to some extent because its susceptibility is low and positive, whereas in diamagnetism, its susceptibility is low and negative. Negative susceptibility, so magnetic lines of force are pushed outside, that is repelled outside. Then ferromagnetic material, more magnetic lines of force will be included inside the material because of its large susceptibility, positive susceptibility.